We have 9 teams that will be presenting today. And all the projects have been sponsored. Industry sponsors are also joining us in person and also remote. Presentations will be roughly 12 minutes and 30 seconds long. And then there will be a 3 to 5 minute interrogation by the judges. Q&A by the judges. As we change over, I'll give the signal to the next team to take the stage, and we will hopefully proceed real smoothly and be on time. So I'd like to call Team 1 to the stage. Team 1, the title of the project is ProScan. Faculty advisor is Professor Shulang Zhao, and the company sponsor is Bioengineering Labs. Students are Lian Orsa, Dorville, Zandre Edwards, Neji Joseph, and Sophia Vilena. Let's give it up for Team 1.
So, good morning, everyone. We're Team 1, and my teammates are
Sophia Vilena,
Zandre Edwards, and I'm Lian Dorville, and today we'll be presenting the prosthetic revolving optical scanner, ProScan, sponsored by Bioengineering Labs Corporation. But first, let's meet Nancy. Nancy was a forklift operator on a local Miami warehouse until last year, tragedy struck. She had a serious workplace injury and unfortunately had to undergo transtibial amputation surgery. And trauma, as in Nancy's case, was just one of the several causes of amputations in the United States. Also, recent papers have suggested that the COVID-19 pandemic may be driving an increase in the percentage of major amputations performed in the clinic. For an amputee, the fit of the prosthesis socket is crucial for their quality of life. And the predominant process of generating the socket is with casting with plaster of Paris or fiberglass. Plaster of Paris captures the complex geometry of the residual limb, and then ultimately that is used to create the positive mold and the negative mold. And ultimately you obtain the socket from the negative mold. Now, poor fit of the socket can have a number of negative clinical consequences, including limited patient mobility, injury and discomfort, as well as the development of negative harmful dermatological conditions. Now, if your prosthesis moves away, then unfortunately a patient will have to go through the whole process from start to finish to obtain a new socket. Thus, our sponsor commissioned us to develop ProScan, a cost-effective residual limb scanner that can generate a positive and negative molds, and thus assisting in the making of a 3D printable socket and that increases access to well-fitting personalized sockets without applying any material to the skin. So this device takes advantage of a number of current market trends, particularly the large size and the growth of the global prosthetics and orthotics market, as well as the segmentation of the 3D scanner market. Now, you might be saying, but there are already 3D scanners in the market. That's true. However, the high initial investment can be cost prohibitive for smaller health establishments in developing countries. So what ProScan does is that it takes this process, labor-intensive process, and then streamlines it to make it more cost accessible to obtain the positive and negative molds. So starting with design, our general design concept is that you combine dynamic mechanical elements and imaging modalities, and as well as software processing to obtain the residual limb model. So we translated the clinical needs into market requirements, and then translated those into design inputs. So our market requirements covered things like prevention of skin irritation, time efficiency of the scan, accuracy, cost effectiveness, and ease of transport and manufacturing. And we considered 3 design concepts and compared them based on their ability to meet our market requirements. And ultimately, we arrived to our selected design concept, which features cost effectiveness, minimal mechanical risk, is inclusive of the 90th percentile of the limb thigh circumference of bariatric patients, and is also versatile for transtibial and transradial amputees. And now, I will hand it off to Sophia Vilena, manufacturing lead, to tell you how we turned our vision into reality.
Thank you, Lian. So the primary components of this device consisted of a set of camera mount rings that we 3D printed in PLA material. Each of these rings had an inner diameter of 0.9 meters, which was to provide ample spacing for the cameras, and it provides a path of rotation for the scanner. these were fixed together using aluminum rods, which were lightweight and hollow to keep the device weight low, and it was also to increase the stability of the device overall. These rings were mounted on PLA plus 3D printed roller wheels that had ball bearings embedded in their centers to facilitate smooth rotation of the device. And this was all put together on a set of threaded rods that were used to fix the rollers in place with vents. A base was designed to hold the whole apparatus in place, and it was designed so that it could be 3D printed in 6 segments. However, for the ease of manufacturing and to progress with the prototyping, we used plywood. And an abrasion-resistant dry roller was used to interface with the inner diameter of the ring, as you can see here. And it drives the entire rotation by friction because it's made of urethane, a lower durometer material. A 12-volt motor, separate motor, was selected for use in driving the rotation of the device due to its positional accuracy. And it was controlled by an Arduino Uno microcontroller that issued commands to the pushing of 2 buttons. 2 buttons were used to incorporate rotation in 360 degrees for the use of 1 camera, and if 2 cameras are used, a 180-degree rotation will be taken. So the cameras themselves are Intel RealSense D415 cameras, which are stereoscopic depth sensing technologies. And these have color capture capability as well as depth sensing capability, and they were fixed to PLA plus adjustable angle mounts. In order to determine the dimensions of the device, we did some trigonometry to based on the scanner's optimal scanning range, and found that the camera angle should be 45 degrees to capture the front of the limb as well as its distal end. And in order to capture that limb, we distanced it 0.35 meters away from the cameras. We conducted simulations on the camera mount specifically, since this was an area of concern since it would be supporting the weight of the cameras, and we did a total static deformation of the piece and found that a total deformation of 0.02 millimeters would occur and a factor of safety of greater than 1 was achieved, indicating that the device was safe. We also did a total lifetime simulation where the lifetime of the cameras is supporting, or of the mounts and supporting the cameras, and found that if used regularly during regular working hours, it would last over 21 years. And so the prototype was fully assembled in the FIU Honors College Edge Lab and using the 3D printers there, and manufacturing was also conducted at the Engineering Manufacturing Center. And ultimately, we achieved the device through very smooth rotation. And now I will hand it off again to Leanne to discuss post-scan in action.
So the post-scan experience first starts with the patient sitting down in front of the device, and the technician or the processist then goes to the computer and starts the scanning script. Then the magic happens. So the cameras rotate 360 degrees around the residual limb, capturing the depth and color information, which can later be processed with the software workflow. So essentially, the software workflow processes the 3D data into a positive and negative model that can be used for diagnostic purposes, for various other purposes. So essentially, you have an RGB, you have color and depth images, which are later combined into unaligned point clouds. Then you have scene reconstruction, which aligns the point clouds into a globally consistent space. Then you have Poisson surface reconstruction, which creates a watertight, dense surface of the residual limb. Then you have post-processing to clean up the model a little bit, and then you generate the negative mold with socket creation using mesh mixer, and then you can go on to 3D printing or manufacturing the residual limb, as you can see here, right here. So now I'll hand it off to Sandra Edwards, Quality Assurance Lead, to tell you how we ensure the safety and effectiveness of our device.
Thank you, Leah. For verification of our design inputs, there are a few specific design inputs that we needed to address. These were under cost, scanning accuracy, and time. The cost analysis verified or cost, which would be later done in this presentation. For accuracy, we had 2 primary protocols that we use for scanning accuracy. But before that, let's go to time. For our first verification protocol, we did 10 scans of 10 different objects and took those samples and took mean times. Our mean scanning time was 14.669 seconds, which was less than our verified requirement of less than 2 minutes, and thus our verification passed. For a second verification protocol, to ensure that our device could accurately scan the 90th percentile of larger limb of these patients, we did 9 scans of a 60 centimeter circumferential hemisphere at 3 different distances. We then proceeded to do an R-square regression curve of these squared fit, and thus we produced a sphere with less than 5% error, with a less than 5% error when compared to the the original sphere. We then did a spherical split to measure the distance, the radial distances from the center of the sphere to all the data points. And then we found that less than 6.5% of all the data points within our samples were within less than 10% deviation from the spherical split, and thus our second verification protocol passed. So then what is it? So then what would a single exam project be without complication? For our third verification protocol, which is our killer test, we did 3 different scans of 3 different geometric shapes, and then after producing our statistical test, we realized that our test failed. We then went into our root cause analysis to understand why these smaller samples underwent so much deformation. We hypothesized that the smaller objects may not be within the optimal range that we required when we preset the device. Also, that the type of preset that we used in scanning may have been the reason why our accuracy was faulty. And thus, we did actual verification and found that the high density, while it did provide a higher fill rate, it was at the cost of misalignment. Then, we realized that our hand preset improved both spatial filling as well as the high accuracy, and thus passed the verification test with less than 4% error. We did additional testing for EMF as well as for voltage to make sure there was no voltage interruptions at the cost for the patient. All the voltage inputs were to our desired lighting and also the manufacturer standards, and thus we passed our verification. Through design outputs, we can realize that we did contactless scanning, we produced a low product cost as well as high scanning accuracy. And now I pass it back to Lee.
So we've gone from design to manufacturing to quality assurance, and now next Joseph will showcase the protocols, and then we'll come back to do the global learning.
So our total cost was $630.69, including the material, labor, and overhead. And for the patent search, we didn't find any existing patent for this mechanical design. Although the novel imaging technology should be developed before seeking a patent.
Okay, thank you. So although Nancy was able to obtain a well-fitting socket thanks to the talented process we have here in the United States, unfortunately, not everyone is as fortunate. Specifically, the 40 million amputees that live in developing countries, especially those who live in developing countries that don't have a formal training program for prosthetics and orthotics. Thus, we have a shortage of trained prosthetists in prosthetic manufacturers in areas that serve underserved populations. So as a result, according to a report by the World Health Organization, only 5 to 15% of people could benefit from assisted products actually have access to them. So now we'll hand it off to Sophia for final thoughts.
Thank you, Leah. So for future work, we would definitely recommend conducting further optimization of the accuracy and improving the ease of use in the software workflow. From a mechanical standpoint, we would also like to incorporate a height adjustment mechanism in the base and make it more comfortable for patients to use, especially for lower limb amputees. We would also improve the circuitry housing, cable management, and also explore applications of the device for different amputees such as transfemoral and transhumeral amputees. So overall, we accomplished a great many things in the project with the help of networking with a wide and diverse population of professionals, and we were able to successfully create a device under $630 that can complete scans in under 15 seconds with over greater than 95% accuracy. So we want to acknowledge and thank everyone who helped make this project happen. They pretty much just, helped make it happen. So thank you guys. And thank you for everyone.
Just an opportunity to delve a little deeper. You can unmute your mics.
You guys are in?
Yes, go ahead, Gene.
Oh, okay. Great presentation, guys. This is phenomenal.
Thank you.
Thank you.
One question. What was your accuracy budget for the device? How much error can you basically tolerate between the actual created surface and the actual person?
Can you repeat the question, Gene, please?
Yeah. What was your accuracy budget? How much error could you tolerate between the printed surface and the actual person?
Our aim was for a 95% accuracy, so less than 5% error would be the case. For smaller limbs or for smaller samples, we prefer the hand preset that result in less than 4% error. For larger scanning accuracy, or the hand preset is fine, but within 5% error for all of them.
Thank you.
Yes, Dr. Namin, go ahead.
So I kind of want to pile on to Jean's question. How did you just establish your tolerances around your design inputs, and how did they affect your overall output and accuracy?
So for the tolerances, we based the 5% accuracy design input on some papers that we were reading that had applied photogrammetry as a scanning method for capturing residual limb contours, and 5% error is their standard that they had used to determine whether or not it would be suitable for producing sockets. For the tolerancing, at least in terms of the manufacturing of the device, we tried to keep tolerances within, I believe it was about 3 millimeters, just to make sure that things would remain within spec and fit together to facilitate rotation. But beyond that, most of the design inputs that we had created were either based on papers that we had read that had applied 3D scanning modality and casting modalities, as well as on some ISO standards that we found for testing the device.
Okay. Any other questions?
Yes. It was very impressive, guys, like, you know, the scope of the project and what you guys were able to accomplish. And I know it's a senior design project, and I am, you know, you went from the user needs all the way to quality assurance. There are also several other elements that need to be taken into consideration. For example, risk assessment. So you set a tolerance, and by, like, you know, you were able to meet that tolerance. But what happens that the 5% that, you know, if it goes, you know, in that error percentage, that 5%, what are the risks for the patients? Have you guys considered that?
Yeah, absolutely. So we considered, so in terms of the device, we always kept the patient in mind when they were using the device. So for example, to minimize, when we did the risk analysis, essentially we looked at the device and said which mechanical part is most likely to fail, and which danger hazards can occur with this device. And we initially had the motor housing, which is interfacing with the electrical components on the side of the patient. But then we changed it towards so that it's facing away from the patient to minimize the low risk, the already low risk that there could be some electrical failure or some other hazards, so that they're minimized from the patient. And I don't know if you guys want to add something to that as well.
We also,
I believe when you said what would the 5% error be for the patient, I believe that was the initial first half of your question. So we spoke to processes within the field, and based on our scanning accuracy, what the patient could face would be mild chafing, but for further scanning, usually when processes do their feel for the prosthetic leg of the amputee, they make the socket a little bit tighter than the actual fit so that it's stuck. And within that 5% error, I think that 5% error would account for within that tightness that the processes would feel. But again, it's always up to the process.
And just to add on to Sandra just a little bit, is that based on the papers that we've read over this project, processes recommend that the fit of the socket is slightly smaller than the residual length, based on their research.
Okay. I'd like to thank Team 1. Team 1. At this time, I'd like to call team number 2 to the stage. Team number 2. title of the project is the Restore VS. Faculty mentor, Professor Jorge Riera, and the industry sponsor is Beta Blue. Team members are Paula de la Plaza, Osmaro Esposito, Carolino Morello, and Nicholas Valencia. Let's give them a round of applause.
Hello everybody, my name is Nicolas Valencia, and with our team, Paula de la Plaza, Osmar Exposito, and Carolina Morello, we present to you Restore VS, a project sponsored by Beta Blue. There's a growing problem for patients with schizophrenia right now. Current treatments that involve pharmaceuticals are highly ineffective. And also, the expensive treatments from invasive treatments are also very not effective. Therefore, our solution is to create a cost-accessible, non-invasive, wearable device that treats the vagus nerve, normalizing dopamine levels, and also restoring the function of the hippocampus. We did this through a 7-point process. However, these are the main takeaway points. First, current modalities do not satisfy the current market requirements. Second, we translated those market requirements into design inputs, and we were able to verify them through testing. And third, this device has a lot of potential for patenting for the future and for many other applications. I'm going to pass that on for Carolina that will talk about the research that we did for this project.
Thank you, Nico. So for the clinical need, we can say that at least 20 million people suffer from schizophrenia worldwide, and the current treatment options include antipsychotic medication, psychiatric intervention, deep brain stimulation, and electroconvulsive therapy. For the business needs, we can say that aside from reducing treatment costs, these projects could actually have revenues that exceeds the $1 to $2 billion, and so the reasons to invest in this project, and as per our interviews, is that there's an increased demand for new treatment options, wearable technology, and willingness of patients to try it. Treating schizophrenia is a challenge to the global scale, and it is known that one's culture can affect the experience they have in regards to a specific disorder. So there's a societal stigma still present, and also a country's available economic circumstances may not permit enough research and advances as a priority. So let's analyze the global perspective in 3 different levels. Thinking about this locally, Miami-Dade County represents the largest percentage of any population with diagnosed mental health issues in any urban community in the United States. And this accounts for $13.7 million towards the care of homeless schizophrenic patients. Nationally, within the United States, 3.5 million people are diagnosed with schizophrenia, and this accounts for an economic burden of $155.7 billion that includes medications, outpatients, inpatients, and emergency services. According to the World Health Organization, around 21 to 26 million people suffering from schizophrenia, and it is cataloged among the top 10 causes for disability globally. After all, the issue is that schizophrenia is not being analyzed as a global perspective, so it is essential for 2 things to happen. First, it's to extend research towards creating new treatment options and pharmaceuticals that are affordable and readily available, and creating educational programs not only for underserved population, but for people with different cultural backgrounds. So with that being said, I'll pass it on to Paula to give us the market requirements for Restore VS.
Thank you, Caro. So after analyzing the market data, we determined the requirements that we must follow for our design. We made a comparison of current modalities for schizophrenia, and we include a patch for the skin, headset that treats neuropsychiatric symptoms, and an invasive procedure. Our main requirements include the resistance of the device to different stresses and environmental factors, also the functionality and interface of electrical components, and the security of the device, only allowing the physician to obtain the treatment frequency and cycles. Other market requirements include the different measures that will protect the user from any overstimulation. Or additionally, the device must be biocompatible, wearable, abide by electrical safety regulations, and must be able to resist any potential neighboring interferences. Now, having said that, our project scope aims to deliver a novel treatment for schizophrenia with a budget of $1,000, and it's going to be using a wearable device that will be delivering 2 million frequencies at the gastric location in the range of 2,000 to 4,000 kilohertz that will create a bit frequency of just 10 to 30 hertz. Now, I said that our device will be using interferential therapy. So interferential therapy is a non-invasive procedure that uses 2 million frequencies as sinusoidal waves that when they interfere, they will create this big frequency. That is what is actually stimulating the region of interest, in our case, the vagus nerve, that is represented as the big region in that image. Now, we use medium frequencies because they prevent side effects due to the skin impedance. And we set our bit frequency to 10 to 30 hertz because it's the bit frequency used today in the clinics for vagus nerve stimulation. Now, our project aims to change the neuroplasticity of the brain and also normalize dopamine levels. As you can see in the image, we have one vagus nerve on each side of our body, running through from our brainstem to the neck, chest, and abdomen. Now, our approach will be sending the electrical signals just from the left vagus nerve to certain areas in the brain. And moreover, we know that vagus nerve stimulation has shown a reduction in hippocampal activities for schizophrenia and depression. Now I'm going to pass it on to Smaro so he can tell us about the design.
Thank you, Paula. So for our device, we constructed some design inputs where we had to apply to in order to make the device work. First, it was applied to IEC standards for electrical components, electrical devices, where we perform stress testing in the form of water pressure, drop testing, and push testing for our device. Additionally, the device must also have a security measure so only the physician will be able to regulate the frequency and be able to output it to the patient. For this, we'll be using a software. The physician will enter a two-factor authentication network with username and password, and also put in the corresponding desired frequency in order to make the device work. Also, our circuit must have a radiated immunity to nearby electrical components, as we live in a technological world where we're surrounded by devices all the time. The device must also have two output channels that will stimulate the vagus nerve through a beat frequency of a range of 10 to 30 hertz. And we expect to get a low frequency here with minimal effect on the skin. In addition, the device will have a switch that allows the user to stop or start the device when they wear it or when they take it off. And the device should withstand a minimum of 3 hours of use for our project, which is the minimum amount of time in order to actually treat the vagus nerve to suppress schizophrenic symptoms. And also maintain enough battery in case there's an overcharge and undercharge to make sure the device will work for those 3 hours. So for this, we came up with some design concepts for our device. Our first design concept was a waist, a belt worn around the waist, where the circuit is going to be encapsulated where the belt buckle would be. However, this device showed to be way too bulky, and the electrodes will have to be eyeballed based to know where they go in the abdomen. Our second design concept was a backpack-like device where we now move the circuit for the upper thoracic region of the spine, which is all more comfortable to wear, and the electrode would move to the left side of the neck. However, the electrodes on the left side of the neck, since the neck is a lot more sensitive than the abdomen, it could cause a lot of rashes and irritation. And also, it was going to be visible to the public, and there's a social stigma there where we don't want people to know that you're wearing the device. Our third design concept will now move into a body vest where we now have straps that move towards the front of the upper left quadrant of the abdomen. However, when performing interferential remedy, it turns out that the interferential stimulation region of the vagus nerve was not successful when having the 4 electrodes in the same position. So now I move it on to Carolina, who's going to discuss our actual chosen design concept.
So our design concept number 4 and our chosen one, like Osmaro said, it's a full body vest with a pocket in the back for the capsule with the circuit location for it to be more protected and not visible. The electrodes coming out of that capsule will position 2 in the upper thoracic spine, and the other 2 will run through the strap adjuster of the vest coming up to the upper left quadrant of the abdomen, right above the diaphragm cavity, and that positioning will allow for better interference. So we designed and simulated a PLA 3D printed capsule to hold 2 nano Arduinos, 2 modules, 2 stereo jacks, 4 100 ohm resistors, 2 batteries, a switch, and all the wiring connection. To be able to fulfill our objective, we need 2 independent circuits connected to 2 electrodes, each outputting 2 different frequencies. So the idea was to fit all of this into a capsule, not make it too bulky or too heavy for it to be easy to carry, but at the same time with enough space to avoid any negative interference among them. We successfully accomplished this by creating a capsule with 2 compartments, one that would hold the 2 batteries and the switch on that same side, and in the other one we soldered together the nano Arduino to the pins of the module. As you can see here, the Arduino fitted under the module. We placed one circuit right next to the other with the respective stereo jacks on the side. And now Nico's going to take us over to the simulations and verifications that we performed.
Thank you very much, Caro. So we ran some simulations to make sure our material was the appropriate selection. We did a drop test and a push test simulation, and both of them passed since the maximum stress did not surpass the yield stress. Knowing that, we went into verification testing after, and we applied a real-life drop test where we dropped the circuit between 1 and 2 meters, and we checked that the frequency of the circuit was working after each drop. And in fact, it did. The mean frequency did not change significantly. Therefore, this test passed. Our frequency output test consisted on our main objective to make sure that the beat frequency is reaching the vagus nerve area of the gastric branch. To do this, we created a phantom model. The phantom model has a porcine dermal tissue that simulates the dermis and the hypodermis of the skin. And we created a mix of gelatin and salt that simulates the conductivity of the muscle. Also, we put a cable in the middle of our phantom model that simulates the position of the gastric branch of the vagus nerve. After that, we measure with an oscilloscope, we apply the frequency with our restore VS, and we analyze the information. We apply the demodulation to our signal. We apply the fast Fourier transform, and we were able to successfully verify that at 10, 20, and 30 hertz of beat frequency, the signal gets to the region, and also it doesn't affect any carrier frequency that we use. Therefore, this test also passed. We did also our security test where we tested the GUI, and only the signal should change if all the information is correct. For example, here the beat frequency is out of range, therefore the signal does not change. It remains in 2010. Now, if we put a different starting frequency and it's out of the range, it does not work either. We verify it and it will still remain on 2010 hertz. But if we put everything in range and the password is correct, then we verify it and the oscilloscope shows that it changes the signal. Now I'll pass it on to Paula that's going to talk about the cost.
Thank you, Nico. So for the cost, we calculated a unit price of $220. Our project cost budget was $1,000. However, our cash outlay was only $373. Since we already had some of the materials and software that we needed, and also we had free access to the BME Creativity Lab and all the verification and manufacturing equipment. Now, assessing our regulatory path, our device will be classified as a Class 2B, which indicates that it will pose a moderate to high risk for the user, and it will be used for more than 30 days. So a 510 pre-market submission will be needed for the FDA to demonstrate safety and effectiveness, while being equivalent to another already marketed device. We identified 2 of those devices as an external vagal nerve stimulator and a transcutaneous electrical nerve stimulator. And now, as Nicolas mentioned, our device has the potential to be patented. We're talking about a novel treatment for schizophrenia that targets the vagus nerve at a specific location. And currently, we're actually working with our sponsor, BetaBlue, on a provisional patent. Now I'm going to pass it on to Osmar so he can conclude with the presentation.
Thank you, Paula. So to summarize our project, we were able to accomplish creating a therapeutic, non-invasive device that will deliver interferential therapy to treat the vagus nerve in order to suppress your schizophrenic symptoms. And we also plan to make this device readily accessible at the global level in both the clinical and the business markets. For future steps, we're looking at a feedback system where the patient can constantly relay information through an application back to their physician in order to see how they're improving or how they're deproving and adjust the frequency as needed through a remote application. Also, we're looking at more medical applications possible with this device due to its use of interferential therapy, which can be used for a lot of other things like such as the immune system and for treating muscle spasms and cramps. We'd like to acknowledge the following people for all their assistance in our project. We'd like to thank our sponsor, BetaBlue, and to you, our audience, for listening and learning about Restore VS. Are there any further questions?
Please.
I have a question. I might have missed this, but is there a particular reason why we're looking within this sort of medium frequency range for these source signals to achieve this beat frequency? Like why the thousands range and not anywhere much higher or much lower than that?
Yeah, so the reason why we chose the medium frequencies first is because it's where the impedance of the skin is not making you uncomfortable. So if we do lower medium frequencies, well, we'll start to get to a point where you will start to feel the stimulation and it won't be as comfortable for the patient. And also those simulations that we chose right there are the current ones using, according to different research papers, for interferential stimulation. So did that answer your question? Okay.
Yes, thank you.
Awesome.
I have 2 questions for you. The first one, What is the expectation on the schedule and the duration of the use of the device as it relates to the efficacy of it? Would a patient be expected to wear this 24/7? Is there a particular, is it good for 2 hours a day and then you're stabilized for the rest of the day?
Correct. Thank you for your question. Based on our design input, we're going to make this work for a minimum of 3 hours, which is it's the amount of time that's needed based on research papers in order to actually suppress schizophrenic symptoms. And with those 3 hours, they're expected to turn it on, put it on their body, and then turn it on and go about their daily routine. And then after the 3 hours, they will be alerted through an application, such as a future application for the project. You can actually alert the patient through their app. It's time to take it off whenever they have the chance. And the device will automatically turn off after the cycle is completed. That's how we have it coded.
Okay. And then the other question that I have for you is, you did a verification for the software, but you really were only looking at security. Did you perform a verification or validation of the software being capable to appropriately set the settings on the device? Did you check that connectivity and that communication between software and device?
Yes. So actually the verification test over there, we were measuring, the oscilloscope was showing the frequency of the actual device. So we did the verification test with our 2 modules, and we made sure that the signal was being sent through the Arduino. This was done through a serial monitor, and we were able to verify this. And it only works when the username, password, beat frequency, and carrier frequency are within range.
And so as part of that verification work of software to device communication, what were your worst case scenarios, or how did you challenge that communication between the two, between software and device, to make sure that you're accounting for any type of error, communication error that may happen between the two?
Yeah, so we tried this with in many cases scenarios. So if the password is incorrect, if the username is incorrect, if there's a space is blank, if you click verify, if one of the spaces is blank, or if any of the frequencies are wrong. So those were our main case scenarios for this verification test.
And additionally, to prevent any bias from us as our, the creators of this project, we went to multiple participants who entered just random information, codes, and everything, passwords, just to see if it would actually work or not. And once they were given the actual username and password, and they put in the numbers within the ranges, the device did work, and the code was inputted correctly.
Okay.
Is there a time for one more question?
Yes, just one more.
Hi. A great presentation, guys, and it's very clean and very to the point. And did you in the design? I really liked where you guys compared 3 different designs and finalize the 4th design. In that process, did you take into consideration of your final design, any failure mode analysis?
Failure mode analysis. Do you conduct any failure mode analysis?
Like the root cause analysis and
In what sense? Failure mode of like the device not working, or
correct.
Transmitting a wrong. Yeah. So Arduino has the ability that when there's something wrong, an outburst of the current. With it will shut off by itself. It has its own breaker. It was part of our analysis. We wanted to either implement a breaker in the system for it whenever it's charging, or if there's a surge of the current, for it to shut down. And Arduino has it implemented with itself. So yeah, whenever something like that happens, it's just gonna shut off. Worst case scenario, you have a switch. You can switch it up. And the good part about this pads is that you can just go ahead and disconnect the pad from the electro wire, and so you're not going to be receiving the frequency anymore.
Okay, thank you very much. And now I'd like to invite Team 3 to the stage. Team 3. Walking Assist Hip Device, sponsored by Bioengineering Labs. Faculty Mentor, Professor Wei Chang Lin. Team 3 to the stage. Team members. Blanca Alonso, Eric Cruz, Annalie Iglesias Gonzalez, Kelly Neer Rojas.
Good morning, everyone. Sorry about noise. Thank you so much for coming today. My name is Kelly Rojas, and I work on a walking assistive device along with my teammates, Eric Cruz and Annalie Iglesias, and Blanca Alonso, for hemiplegia patients. I would like to start this presentation by showing a quick video of the medical issue for our project known as hemiparesis, which is the loss of body movement control on one side of the body. This occurs in up to around 88% of post-stroke patients, leading to unstable gait and reducing their motor function. These patients often go through physical and psychological pain because of the medical issues that they face due to this situation, particularly though when it comes to walking. Our target population is hemiparesis patients with loss of body movement control, specifically on the hip area. And the reason why we focus specifically on the hip area for this project is because based on physical therapy study done in 2012, around 40% of the power consumption done when walking is done by the hip. So targeting this area, the hip area, may be significant for the hemiparesis patients. Some of the current devices currently available to help these patients become more independent include the wheelchairs and rollators. However, this may not help to restore function. For the business need, we found that during the COVID pandemic, the walking assist device market was around $6.1 billion and expected to reach around $7.3 billion by 2027. These markets are oriented to growing industries such as insurance companies and private care, and research to invest in a project like ours include the continuous passive motion therapy demand and the increasing demand for user-friendly devices. And as shown on the bar graph, we can see that when comparing our devices to competition, Exobionics and Kyogo exoskeletons, and the Honda walking assist device, our device is more affordable at $1,155. Therefore, our proposed solution is to design an active, adjustable hip device that assists hemiparesis patients by targeting the hip and thigh muscles, specifically to help them eventually improve their walking stability and regain motor function. One of the main reasons why exoskeletons are often used in neurodegenerative disease rehab is because exoskeletons often help to target the residual motor function, helping to increase muscle mass and improve the walking stability. Some of the most important market requirements and design inputs that we developed for this project include the valid longevity of at least 2 hours for a full therapy session, and adjustability system of at least 2 connections for the device to fit different body sizes. These market requirements and design inputs also help us to come up with our design concepts. For this project, we developed 3 different design concepts, and our winner, design concept number 3, has an electric rotary actuator that focuses on targeting the affected side of the user. And having one actuator also helps to make the device detachable and reduce the overall cost and weight of the device. For the design concept number 3 and the Arduino and the prototype, we created an Arduino program, and here's how the program works. When the healthy leg piece of the device has a turning system that works along with the rotary encoder. Whenever the healthy leg moves, the rotary encoder records the number of steps done by the healthy leg. And this information is then sent to the actuator, which mimics the number of steps done by the healthy leg. In other words, the healthy leg mimics the healthy leg, helping to stabilize the gait of the user. And as shown in the other video, we can see that we were able to make our device detachable and adjustable. And now my teammate Eric will present more information on the biomechanics simulation that helps us to pick our actuator.
Thank you, Kelly. Before selecting our electric rotary actuator, we conducted proper research on the biomechanics of the gait cycle. We used simulations through MATLAB as well as free-body diagrams by using a 220-pound and 185 centimeter tall person. The results of these simulations concluded that the highest producible torque from a person with these physical characteristics is 37 meters. This value is a torque that is needed to help lift this person's leg. So as a result, we searched for an actuator that was capable of reproducing a value like this until we found one, in which it is capable of reproducing 50 newton meters of continuous torque and 100 newton meters of maximum torque. In order to ensure the safety of our device, we conducted stress test simulations on SolidWorks, and the parts that you see here are the most ideal parts of the device. The factor of safety was measured for each part, in which the minimum factor of safety was greater than 1 at each face. However, you will notice that with the leg part, the yield strength is slightly lower than the maximum yield, meaning that this part is to be susceptible to deformation. So in order to bypass this, we formulate.
Can you hear in the back? Can you speak up a little bit?
Louder. So in order to bypass this, we formulated several solutions in which we go to help increase the factor of safety of this part, like changing the material, increasing the filament, and even increasing the thickness of the parts. And as for the technology assessment, the following components of the device are shown below, in which the material that we picked is an 80% PLA and 20% carbon fiber filament, and we use to 3D print our parts. The junction box in the back contains our electrical components. On the right here, you see our electric rotary actuator, and on the opposite side is our rotary encoder. For our device, we developed several verification tests to ensure that our design inputs and outputs are corresponding with each other. And so, I hand that off to my teammate Anali, who will help explain the results of these tests.
Thank you, Eric. So our first verification consists of measuring the various capacity of the actuator and Arduino components using a multimeter to ensure our device can perform for at least 2 hours of continuous usage. As shown in the graph, the actuator reached 3 hours of continuous use with and without load, and the voltage decline shows that the battery still has more power left to supply, passing the verification test. To ensure our device is safe to use in a world now often surrounded by electronic devices, an electromagnetic interference test was performed using an EMF tester tool. From different distances, we got 0 values for both electric and electromagnetic interferences, passing the verification test. Our next verification involves taking the longest and shortest measurements of the adjustable sections in our device. The measurements were taken using a ruler and a measuring tape. The resulting ranges for the hip frame from 16 to 22 inches and the leg section from 5 to 9 inches fell into the required ranges stated in our design input, passing the verification test and proving that our device is suitable for different body sizes. Range of motion was verified using a goniometer. When wearing the device and walking, the maximum angle of flexion 57.4 and extension 19.8 were captured. These results surpassed the maximum angle of flexion and extension needed at the hips when walking. A sample of the device structure was placed into an oven at 106 Fahrenheit and into a freezer at 1 Fahrenheit, based on the United States climate report. An elasticity test was performed, and a 40 to 45 pound force was applied, and the piece handled that force without any deformation, passing the verification test. To verify the weight of the device, a scale was used, and the whole device was found to be around 17 pounds, which is less than the maximum weight that the person can withstand based on the lightweight definition by the Collins Dictionary. As a summary, all the verifications were passed successfully. To remove any doubt as to whether this device will assist the patient in walking, an electromyography test was chosen as our killer test. Electrodes targeting the hamstring muscles measure the muscle activation when walking with and without the device. Looking at the mathematical integral of the absolute value of the raw EMG signal, our results demonstrate that the effort produced when reaching the maximum angle of 45 degrees when walking, as shown in figure 2, correlates with the minimum effort produced without wearing the device and reaching the same maximum angle as shown in figure 1. These results demonstrate that our device can assist the patient when walking whenever there is not enough effort produced in the hip muscles. Now I'll pass it on into Blanca, who's going to take you into the product.
The following is our cost to create this device. Our cost of materials is $1,013. Upon adding the cost of labor and overhead, our total cost is $1,155. The global prevalence of stroke in 2019 was over 100 million people. After stroke, hemiparesis is common. This shows that it is a major cause of disability worldwide. The global market for stroke management devices is rapidly expanding, implying that the market for exoskeletons may benefit from this as well. We took all of this into perspective, and so we made our device as best as possible. We made our device adjustable, so any body type or size can use it. We also made our device as affordable as possible. Since hemiparesis only affects one side of the body, we used one motor. This would reduce our product costs. We also wanted this device to be able to be used for the left or the right leg, so we made our device interchangeable. We passed many of our goals. We made our battery life greater than 2 hours. We made the device adjustable. But in the future, we can always make some improvements. So we would like to improve the device's ergonomics. We'd like to see this device being used for other medical applications. And we would like to use this device with an app for wireless communication. We would like to thank the following for all their contributions and efforts in assisting us with this project. We would like to thank you all for listening to our presentation. We will now take your questions.
We have time for just 2 questions. Judges.
So what were the trade-offs that you performed on for your device to lower the price, the target price of your product in comparison with other products on the field?
You lowered your price. What did you sacrifice, if anything, for a lower price?
I would say the weight, the resources that we use for our device.
Were off the shelf
Yeah.
pieces. They were off the shelf pieces, so we had to work with what we had. But we reduced like the motor in that case, but besides that, there wasn't much of a difference compared to others. It was just mostly like the device, the ergonomics that we had to design.
We had to try, we tried to find an actuator that was able to handle the force that we needed at the hips in order to lift the leg. And it was really hard to find because most of the actuators right now in the market are like very bulky and very heavy. So that was one of them.
Okay. All right.
Thank you.
Let's, do you have another question, Jean?
I'm saying the same thing.
Okay. All right, let's give it up for team. This time I'd like to call team number 4 to the stage. Trophy LD, sponsored by Activoris, Medical, Pharma and Food, faculty mentor, Professor Josh Hutchison, team members Ricardo Cabezas, Anna Dramanov, Carolina Gulen, Daniel Peño, and Alex Trinidad. Please take the stage. Team 4, take it away.
Hello everybody, my name is Ricardo Cabezas, from group number 4, representing to you Profile D. Every year, around 300,000 people in the United States and 85,000 people in Europe contract Lyme disease. Lyme disease is caused when an infected tick with Borrelia bacteria bites a person. And this person can start developing symptoms such as fever, such as skin inflammation, joint pain, arthritis, among others. Lyme disease is caused because so the available treatment right now are antibiotics. For those seems to be related with persistent symptoms that can last up to 10 years. With the rising cases United States and Europe, there's not approved vaccine or prophylactic treatment that can prevent or treat Lyme disease. So doxycycline is taken preventively, but is not recommended for kids under 8 years of age. So there's a problem because the Lyme disease incidence is highest between ages from 5 to 15 years and 45 to 55 years old. Our sponsor developed a handheld device that can stop the bacterial infection. But this device was only meant to be used in oral cavity and not in thick bite sites. So, moreover, this device, it does not have a removable tool. This device does provide feedback to the user and can be only self-applied. That's why we come up with a solution, Profile D. You can see the current modalities, and our device provides an actual removal tool for ticks, provides a feedback, acoustic and visual to the user, and the therapy can be applied to more than one person. Now that is going to talk about the marker requirements and design inputs.
So to summarize our marker requirements, first we wanted our device to be able to be handheld and to be able to be portable. Next, we wanted the interface of our device that meets the user's skin to be able to accommodate the most common sizes of tick bites, as well as the common regions of the body where ticks tend to bite. We wanted to ease the process of tick removal for our users, and we wanted to deliver a current that's safe and harmless to our users. Moreover, we wanted to deliver an amount of silver that must not cause side effects, but at the same time must be effective in killing bacteria and doing its job. We wanted to communicate to the users that therapy is ongoing, and so we proposed that we have a visual and an auditory feedback component in our device. Based on our market research, it suggested that our therapy should be delivered in 30 minutes or less. And finally, we wanted the enclosure of our device's electronics to be able to be resistant to factors of the outdoors, such as humidity, potential water exposure, and the particles in the air. So with these market requirements in mind, we proposed appropriate design inputs that would fulfill these things. And now Caro will go over our design concepts.
So we first developed these 3 design concepts, which were small enough to be handheld, but they were still kind of boxy and uncomfortable to grab. We didn't like them that much for that reason. And also, they had the problem of the silver anode shape and size. They wouldn't be ideal to reach those hard to access parts of the body where ticks like to bite. So we came up with a preferred concept. This one has a cylindrical shaped body, which makes it much more comfortable to grab and hold. Moreover, this one has a separate part holding the therapy, which has a smaller diameter that will reach, for example, behind the ear. In terms of components that we're choosing, we prefer PLA just because it's a proof of concept application, and PLA is commonly used for that purpose, as well as being very easy to 3D print. We also chose a V-shaped tool to remove the tick, and it's the case in this compartment, since tweezers are known to crush the tick's body when they pull it out. We use fine silver coins to manufacture piano. Silver is known to be the best conductor of electricity out of all the metals, and also when used in solid form, it's also shown to have less toxic effects than silver solutions. A copper wire was used to manufacture piano. Copper is very vigorous, has a low cost, and has high resistance to corrosion. And the Arduino Nano was the microcontroller of choice since it offered a sufficient number of pins that we needed for this project. We're using alkaline batteries since they have fewer disposal restrictions than other batteries, so the user can replace them. And we're using 2 voltage boosters to reach the correct voltage that we needed in order to be able to apply the therapy in under 30 minutes. Now, Anna will talk a little bit more about design specifications.
Thank you, Carl. Following the market requirement of being handheld, the device is 22 centimeters long, and it has a comfortable cylindrical shape to hold with a diameter of 5.6 centimeters.
Projection, please.
Louder. The outer shell of the device consists of 3 parts. It has a top part,
bottom part and the head. The top and bottom part are held together with the screws, and the head snap fits the curvy portion of the bottom part of the device. The device also has a ticket removal tool with a V-shaped tip, which is located in this compartment, and it is secured with a plastic cap. As you can see from this side view, the top part holds the PCB that was designed by us, and it holds all the electrical elements on it, which includes two LEDs, switch, push button, buzzer, two voltage boosters, and one Arduino Nano board. The bottom part houses the battery holder for two AA batteries. The head has silver anode and copper cathode, and it is connected to the main circuit of the device with a long coil line. We use Arduino Nano to program various functions of the device. So it is used to program the start, the powering on of the device. It's also used for signal when the therapy starts and ends, and also to program the length of the therapy. To start using the device, it's first should be powered on with a switch. When the electrical switch is flipped on, the user is signaled with one buzzer beep, and the green light turns on. When the therapy starts with a push button, the user is signaled with two buzzer beeps, and the green light is constantly on. And when the therapy stops automatically to avoid treatment, the green light turns off, and the user is signaled with three buzzer beeps. It is important to know that before applying the therapy, if the tick is still present on the skin, still attached to the skin, the user has to remove it using tick removal. And now Kara will talk about simulations.
So the most important thing that the device needs to do is deliver silver to the dermis where the bacteria that cause Lyme disease are located, right? But we couldn't verify this since we cannot deal with human skin. We wanted to do a simulation that would predict that at least silver ions are capable of reaching the dermis, encounter the bacteria, and they would do this in under 30 minutes. So for that reason, we researched thickness of the layers of skin that silver ions need to travel through, especially epidermis and dermis. We researched how fast they will be traveling through this thickness, the diffusivity of silver ions, as well as other properties such as the electric conductivity and permittivity of skin layers. We also considered design specifications such as the dimensions of the cathode, the anode, the separation between them, the voltage gradient at the skin anode interface. And with all of this and solving some electrostatics and mass transfer equations, we obtained these results using complementary physics. The electric field lines are showing the most probable paths that the silver ions would take, and these are very good results because they indicate that indeed the silver would encounter the bacteria in the dermis. And this last picture here is showing that the silver ions would fully saturate the skin domain where the therapy is applied in 4 minutes. In terms of manufacturing and prototyping, the anode was manufactured using 3 fine silver coins using the delta die casting method, and the cathode was manufactured from a 3 millimeter diameter copper wire. The shell of the device was 3D printed using PLA, and the PCB that we used was designed using the ECEDA software. Now, Danny will talk a little bit about the verifications of it.
So we began our verification testing by first ensuring that our device would meet the ergonomic standard for handheld devices. So we weighed it with an analytical balance, and we measured it with a caliper, and it passed this test having a lighter weight and smaller dimensions than what is standard for a handheld device. We measured our device's head diameter to make sure it was between 15 to 27 millimeters with a caliper, and it passed this test having a diameter of 20 millimeters. And we measured our tip removal tool's thickness to ensure that it was below 1.5 millimeters in thickness. This was done with a caliper as well, and it passed this test as well, having a thickness of 0.6 millimeters. Next, we performed an ingress protection test to ensure that our device would function properly even after exposure to dust and water. So the way we did this is we subject our device to talc powder using a blow dryer, and we used a shower head to simulate soft rain and the splashing of water. and our device passed this test with an IP rating of 5.4, which signifies that even after exposure to limited dust entry and the splashing of water, our device still functions properly. Then we performed the humidity resistance test, where we placed the device next to a humidifier, and we used the hygrometer to measure the conditions of the surroundings. And it passed this test after being exposed to the humidity, the 90% relative humidity. Next, the most important test that we performed is one to ensure the accurate and intended release of silver. So the way we did this is we used a piece of porcine belly skin and we applied our device to it. And we measured how much weight was lost from the device for every hour for a period of up to 5 hours using an analytical balance. And as you can see in the graph, our observed results were very similar to our calculated expected results. And seeing as how we had an R-squared value of about 0.9 and our null hypothesis fell outside the 95% confidence interval, we concluded that we passed this test as well. And the final test that we performed is we used a multimeter to ensure that the current being released was less than 5 milliamperes and stable and consistent. And we passed this test displaying a current of 1.07 milliamperes at the skin and add-on interface. And now Alex will go over the cost analysis of our product.
Thank you, Danny. So with a material cost of $42.62, $70 of labor for 5 hours at $14 an hour, and $33.97 of simplified overhead, our total cost for the product was $146.59. So because our device comes into contact with human skin and is moderate risk to the user, we expect it to be classified as a class 2 device, which is subject to general and special controls. It also has to follow post-market surveillance and special labeling requirements. We do not have a predicate device for the FDA has not approved a predicate device, so we are not exempt for a pre-market notification. And home use devices they have to undergo extensive testing for electrical safety and biocompatibility. Lyme disease is endemic to many parts of the Northern Hemisphere. And with our project, we aim to help reduce the effect of the most common disease spread from animals to humans. We also want to make this device in the future reduce the cost to make it more accessible to all populations. So over the course of the past 2 semesters, we've been able to develop our design, model and simulate our device, and manufacture Profil-D to remove ticks and deliver silver ion therapy. We also successfully completed all of our verification tests to verify we met RDIs. In conclusion, Profil-D is our new prophylactic treatment for Lyme disease, delivering silver ion therapy to the skin. In the future, we would like to make this product maybe smaller and cheaper to make it more accessible. We'd like to thank everybody who helped with our project, and we'll take any questions.
We have time for 2 quick questions.
I have a question. Did you guys perform any kind of FMEAs and application FMEAs to identify any usage risks and have any correlating mitigation steps to those risks?
I understand the question. Did you consider the risks to the users and mitigation for that?
Yeah, so performing some sort of FMEA on the usage of the product to patients and if there was any identifiable risks and mitigation steps to those risks.
Yeah, an identifiable risk was overtreatment with silver. Silver is really considered to be non-toxic to humans, but if delivered if overdosed, if delivered in a high amount, it can lead to argyria, which is blue discoloration of the skin, but it's permanent. It's not cosmetically pleasing. And to do this, what we considered was just having the therapy, programming the therapy to just end automatically after the time that we knew and we calculated that it would deliver a sufficient amount of silver. And with this, that risk would be mitigated. And another risk that we were considering was just crushing of the ticks, because that has been shown to cause increased infection. And that happens when you use tweezers. That's why we mitigated this by just switching and choosing a component such as the V-shape tool that would mitigate this risk.
Dr. Thompson, you there?
Oh.
Go for it. Go ahead.
All right. So the duration of the treatment is supposed to be 30 minutes, right?
No. It's, yeah, I don't want to take it. It's supposed to be under 30.
Under 30 minutes. Okay. So really quick, if we go back to slide 19, when you did the verification testing for the safety silver dosage delivery, you looked at it over time, and you know, you say you passed the test, but if you look at the curve, or if you look at the line of what you're actually observed for the first 50 minutes, actually almost for the first 100 minutes, you were well under what you were expecting to deliver. So, I mean, I think it's a great product. It looks very interesting, but it looks like you have some troubleshooting to do there, right? Because, you know, how would you go about mitigating that delivery deficiency in those first 100 minutes?
Well, we are
in this particular verification, we're overdosing the porcine skin, so we're delivering many hours of treatment where when it's not necessary. We just wanted to see that we could estimate the silver loss by the device.
Just to add on to that, I know what you're saying. That first point, we are attributing that to just human error, and also to the balances that we were using. Because the issue is that we had a minor complication that day in the lab, and so because the rest of the points do follow the trend and are very close to the expected results, we are attributing that first point to error. In the future, this is not verified the way we did it. We did it by mass loss from the device, and the mass loss is attributed to the silver loss that we are having. But in the future, this is actually done by observing the tissue under a microscope and seeing the silver that is released to the tissue. But yes, what we were considering there is that if the results are close to the expected results, the expected results, then the calculations that we were using Faraday's law of electrolysis, then that is validated, and we can use this equation to calculate the time of the therapy, considering what we want to deliver for silver. And that's what we passed.
Okay. All right, let's give it up for team. I'd like to call team number 5 to the stage. Team number 5, ampoule scoring and sealing machine, sponsored by Panther Biomedical Medical Packaging Solutions. Team members: Elizabeth Chen, Anna Valencia, Jesus Alvarado, Maria Salome, and Gisela Lopez. Let's welcome team number 5.
Good morning, everyone. We would like to thank you very much for your presence. First of all, my team and I would truly appreciate you guys being here since early. We're team number 5, and our device is called ampoule scoring and sealing machine, and we're sponsored by Panther Biomedical. First of all, I would like to invite you to understand the need and importance of these projects. For those who don't know, the ampoule, what is an ampoule? It is a glass vial that is meant to contain a sample. So, I'm sorry. Okay, it's a glass. It's a glass vial that is meant to contain a sample, and maybe you've seen it before. Like when you get an injection, the medicine comes in an ampoule, then you break it, and it breaks in the scoring point. Okay, so basically our goal is to supply the medical industry with an automated process that scores and seals ampoules of different sizes. The market background is expected to reach 6.27 billion in 2026. And by designing this automated process, we don't only provide a low cost efficient solution, but we also lower the safety hazard risks. And we promote the ampoules as a reliable option for diagnostic testing. So basically, in other words, we want to promote a cost-effective automated process for our startup companies for their product design before they start investing in a large assembly line. So here you can see our market requirements that are tailored to our design inputs. First of all, we should have a preset point, which is where the ampoule should be loaded. And oh, by the way, this is I'm sorry. So this is the preset point where the ampoule should be loaded, and this hopper that is on the 15-degree angle will help it like load it. So this Oreo must maintain the weight of the ampoule, and it's gonna be the stepper motor is gonna help it like rotate. So we create a phone Bluetooth app that will control the load amount of ampoules that will be scored and sealed. For the sealing, we have the tubing, which should be 3.5 millimeters, and then the heat gun must exert a temperature between 90 to 160 degrees Celsius. This is a lazy Susan, so it must rotate in 90-degree intervals for each station. So basically, we want to produce a small-scale automated process of ampoules in order to eliminate most disadvantages of large-scale automated process by providing a low-cost, but a small machine, and a small machine that will be space efficient and that will produce ampoules that will be scored and sealed in different sizes. Next, Liz is going to talk about the design inputs. Design concept, sorry.
Thank you, Gisela. So as you can see here, after going through our market requirements and our design inputs, we began our design concept evolution. So over here, we see our initial design concept, followed by design concept 2, and our final design concept. This is a general overview, which I will now go into more depth about. So starting with our first design, we have our integral station. So as Gisela was mentioning, we have our loading station, which actually is right over here. We have our scoring station, our sealing station, and our unloading station. So within this first design, you can see here, we actually have 2 of these hopper systems right over here. So you can see there's 2 Oreos set up, and we realized after extensive simulations that there wasn't a purpose for having these 2 setups. Actually, having a 1 is very good because it keeps it concise and keeps it simplistic. So we have our main turntable right over here. This is powered by a stepper motor, and it's a turntable, so it allows the ampoule to go from station 1 to 2 to 3 to 4. We have our second station of scoring, which Gisela was mentioning a bit about as well. So this creates a standardized scoring point that we need within the ampoule itself. We need to be able to break that ampoule tip at a precise location, and to do that, we have our second station of the scoring station. Initially, we did have a photo sensor system, and that was going to allow us to figure out the height that we needed to get to score the ampoule out. However, with budgeting reasons, we could not employ the system, so we devised a new system in order to combat this issue. After that, we have our sealing station. So our sealing station is used to encase the ampoule tip in a plastic material. Within this first station, we use a material called Tygon. So Tygon is a very cumbersome material. It's pretty difficult to work with, and it has a very specific diameter. So after we did a few research and a bit of initial testing, we realized that Tygon wasn't going to be a very good use within our project, and it caused us to evolve our design a little bit more. So this created a fifth station of heating. So we realized the best material that we could use was polyolefin. Polyolefin is a heat shrink material. So with a heat shrink material, it allows us to have a wider radius that we can work with so that we can tip our ampule properly. And we heat the system so that we can shrink that ampule tip to the correct diameter. Within our final design, that's what I was speaking of before, where we integrated the two systems together and we had our final system right over here. Through simulations, we've also realized that our original design had an open system just like this. It was a mirrored system. So we realized that after quite a bit of load of ampules would come in, we needed to employ a back wall or the ampules would end up spilling out of the system. In order to combat that scoring issue that we had initially, we introduced a phone app to mitigate those systematic concerns. So we were able to integrate the phone app to turn on the machine or turn off the machine, select a specific ampule load, as well as change the distance of the scoring location. So now that we went a little bit over our design concept formulation, we'll go into the technology assessment of the materials that we use. So after extensive research, we realized that the best materials would have been, or have been, our ABS, which has been used for our 3D printed parts, such as the tipping station here, the bracket for the scoring station, and Oreo servo motor right over here. Stainless steel, which was used for our rods over here. Steel as well for our system to connect the towers together. Cast iron for the bottom stool right over there. High density polyethylene, which is this material over here in starboard, so it was a very sturdy material for us to use to build our base. Brass to form the couplings to connect the tower to the table, as well as aluminum also for the tower connections. So now after going through the materials, we'll go into our manufacturing process, which Rita will now explain.
Let's push mutual. Oh, that's what it's Gotcha. All right. So as you've obviously gone over, we have various stations here, and everything is basically done either at carpentry shops, fab shops, or the machine shop here across the tiny building to the north side of this building. For the most part, it's just blood, sweat, and tears, which I can thank my entire group of putting painstaking efforts. All right, trials and tribulations, because we all suffer through this somehow, some way. I'm sure that's a unanimous decision for every group. So that being said, we've already got over materials. Custom parts, we're going to thank Luann over there for 3D printing. You see various parts all around that we had to make sure. As you saw, these were also custom, by the way. We had to outsource for these because it's not necessarily so easy to find. The original machine that we had to work with would make those, but because we're no longer working with that machine, we had to kind of go around. So we can go ahead and focus more importantly on our actual design. Can you do this for me? Thank you. So our first, I just want you to understand, before we go into each individual station, is that our machine is comprised of 3 different sections. We have a fixed base that we put onto a rolly thingy, or a dolly just for mobility, but it's a standalone table. We have a station base that holds all of our stations individually, and it's supposed to be sturdy. Our turntable has 2 systems here. It has our ampule system, and then it actually has a rising system that'll bring up ampules to adjusted heights. So there was mentioned a phone app that controls load size and ampule heights. That's the whole purpose of this guy here. It's so that whenever the startup company is trying to decide what they're going to do with their product, if they want a smaller ampule or a taller ampule, they can put it into the app, and then this guy is going to rise however inches or centimeters need be to accommodate for whatever station it's heading over to. So if that's understood, we can go ahead and continue on to our first station, which is loading and unloading. As was mentioned, these guys are combined. So if you can kind of guess, loading is the top guy and unloading is the bottom guy. This gravity works really well for some things. And the ampule just slides straight through into what we have, a claw system here. Our claw will grab onto our ampule, supposedly, and bring it over. Hopefully I don't drop this. to where our rising system will come up and catch it. A linear actuator will extend our ampule over and hover it to where our rising system can meet it. Now, once it's fully loaded, our turntable is going to come over and bring it to the scoring section. The scoring section will rise to whatever needs to be height, and a linear actuator, well, first the stepper will align the carbide blade to the ampule, and a linear actuator will extend so that when our rising system comes through and meets the carbide blade, a certain amount of pressure, technically it's 14 psi, will come through so that it doesn't shatter the glass, but it'll create a nice little scratching or etching alongside to standardize a breaking point during administration. Now, how do we make that etching point happen? That's that secondary system I was talking about here on the turntable. This will actually turn the glass so that the carbide blade doesn't put too much pressure on it, and that will kind of mitigate any premature fracturing. So most of these ampules, actually all of these ampules, are vacuum sealed. Any sort of infraction or like malalignment of the ampule will either cause a sample to be faulty, or it'll break early, or it'll just like not work entirely, or cause excess glass, and that's a safety issue. So we kind of had to accommodate for those concerns, and that's why we decided to make the turntable the one that manipulates the cutting or controls the cutting foremost. Okay. Now the ampule will go back down just for safety's sake, and then rotate to our tipping station. Now our tipping station is really cool. He comes forward and backwards to accommodate for whatever, and which is used via a linear actuator, and then our ampule will come up to this custom-made funnel and an extruder, which was very hard, by the way, because extruders usually use solid filaments. This is hollow, so it collapses. Thank you, Jesus, for figuring out that problem. Would come out through and be brought onto our ampule. A scissors will slice the heat shrink so at whatever aforementioned height that you can program into the app. So it will accommodate for whatever ampule tip. If you notice, some are 2 inches, some are 3 inches. So it's whatever the company needs. Now, once that happens, the ampule will yet again drop for safety's sake, and move to our heating station. Heating station is actually really nice because it doesn't have to come back up. The heat shrink gun just shoots the heat down. And the reason for it not coming up is because borosilicate tips will melt a lot easier than the actual borosilicate base. So we don't want the top to melt into the heat shrink if our heat shrink gun has too much heat. So once everything has been processed, that means our ampule has been scored and it has been sealed. It's now ready for unloading. This point, it's basically the same as loading, only that it's friction reverse. So the claw will come out, hug the ampule, say you're mine, go over to unloading, and then drop it. Via gravity, it'll come over to the base, and that's why you see this back table here, to catch the ampules. And now everything's ready to be packaged and sent off to whomever has ordered that. So,
Let's try to wrap up.
that being said, I think I'm done. Let's do some fun.
Alright guys, so here we run simulations in the parts that exert the most weakness in the machine, which would be the gearboxes and the inner rising gears. Any gear in this table correlates to these inner rising gears. That includes the risings and the spinning ones. We can see that in the stress test, the most stress is exerted in the inner corner of the gears, and this is about 10,000 times beyond the yield point, so we're pretty good with the ABS material. And then the gearboxes have the same maximum stress point, but it would be in the place where it's the thinnest, as we can see by the color coding. And this is also about 10,000 times beyond the yield test, so that's good. Then, if we look at the displacement, the points change a little bit. While in the gearbox, we see that the red areas are still in the more weak points. In the gears will be in the tip, because when the force is applied to the tip of the gears, this could be displaced. However, this will happen over time, and when the force is continuously applied in one single tip. However, this doesn't happen because the force is distributed along the tip while development goes. And here we see the preliminary pictures of the design. You can see how many things has changed. Well, we're still pretty much the same in a lot of stuff. The stability was added using the brass couplings in the bottom, and also using the platform that holds both hoppers aligned to each other. Here we can see that the ampule colors changed a little bit. They were used to be like PBS, now they were custom made and 3D printed. And we can see in the bottom the tipping station. This was the most radical change. It was supposed to be a simulation of a 3D printer extruder. However, she mentioned that the extruder is supposed to feed not hollow tubes, and this is hollow. So when pressure is applied to it, the tube gets deformed and it doesn't get extruded. How do we solve this? We force the tube to its original form in the top and in the bottom of the extrusion process. And in the center, we apply maximum pressure to deform it. That way, it gets extruded by the maximum friction between the motor and the cogwheel. Now, the verification test we were able to do and pass these three that you can see here. Loading and no longer angular inclination, we were able to verify this by the use of a digital protractor by measuring the angles at what the hoppers are inclined. The lazy Susan motor rotation test was passed by measuring many times how the motor rotates with respect to the whole table. And the heating gun, we just used a thermometer and we localized the heat that the gun was exerting, and it was proved to be within the range that we decided. Scoring test and tipping test were still in progress. So stay touched. Cost analysis. Now, I'm going to go over the cost analysis.
Thank you, Mr.
Try and wrap up.
Yeah. Our budget for this project was $2,000. We estimated that the materials would be $1,165. We also estimated the price with 5 workers working at $25 an hour. And therefore, our total cost would be $1,433. Ampules are used all over the world, and they're very significant in the medical community for ampule storing and shipping. This market has grown significantly due to the COVID-19 pandemic. So being able to make a machine that is cost effective for scoring and sealing of ampules will be very significant for the vaccines. The goal of this project was to create a cost effective machine that will be able to score and seal ampules for small industries that need customization for different size ampules. These are the ISO standards that we utilize, which include the electrical standards, the tool machine safety, and risk reduction practices. Finally, our future works, we hope to implement better communication between the Arduino boards and better power supply. Thank you for listening, and we would like to acknowledge all the people that made this project possible. Any questions?
Yes, we have time for one single question.
Yes.
Quick question. What is the throughput of your current system, and what are things that you can evaluate to increase it?
Can you reiterate that, please?
Sure. What is the throughput of your system design, and what are things that you could do to increase it?
How many sealing of ampules can be done per minute or per hour?
That would depend actually on the company itself. The point of the Bluetooth app is that you can adjust your load size to whatever you want. Like if you're doing experiments on something, you might want a smaller load. If you already have massive production in mind, then you want to do a larger load. That's the idea of the Bluetooth communication.
I think she was asking how many, what's the upper limit? How many ampules can be cut, scored, and sealed per?
How many ampules you can, or how many tips you can pull out of this guy then?
So it's limited by that. Okay.
That'd be the only one, yeah, because everything else is electrical.
All right. Thank you very much.
device.
Thanks, give you
Yeah.
the
Thank you very much. That was team number 5. I'd like to call team number 6 to the stage. Team number 6, secure adipose tissue, seat, faculty advisor, Professor Zachary Danziger, and the industry sponsor, Tag 3, Bottom Line MedTech. Please come to the stage. I'd like to introduce Lygia Camilla, Samuel Gita, Schneider Jean, Monica Pasquarella, and Daniela Zakina.
Hello, everyone.
Rest, please. Keep it down the back.
Thank you for the introduction. Hello, everyone. As mentioned before, we're at 6, and our sponsor is Biomedical Engineering, and our project is secure extra adipose tissue, also known as CT. So CT will be used for patients who are considered obese to severely obese. But before we get into details, I would like to share the term panicus, which is the overhanging abdominal layer of subcutaneous fat, and in some cases, it's a ventral hernia. As you can see in the image, the panicus is covering access to the pelvic area. Therefore, the correct handling of the panicus is essential to reduce medical complications. Obesity has increased by 12%, as well as an increase of treatments such as laparoscopic procedures and bariatric surgeries for complications related to obesity. The oversized panicus limits the access and visibility to the pelvic area, which is a surgical site for these procedures. The thyroid traction is one of the most commonly used methods to expose the pelvic area, but it can cause respiratory problems. As you can see in the image, there is a panicus classification of grade to grading, in which grade 5 can go all the way to the ground. And the average weight of a panicus with the patient standing ranges from 11 pounds all the way to 120 pounds. Some great competitors are Clinical Innovations and TZ Medical with a retractor that exposes the pelvic area. As you can see in the graph, from 2018 to 2026, it is expected for the surgical retractor market to grow in a variety of different surgical departments. And what will allow this market to grow is a product that eases discomfort and minimizes the risk of surgical side effects. So the problem statement is based on the survey made to the nursing staff, in which we have to improvise a device using silk tape because the current methods cause adverse effects on patients and use of staphylor retraction. So our solution is to create a device that can retract a panicus grade 1 to 5, will expose the pelvic area without using staphylor retraction, and will not cause adverse effects to the patient. Now I'll pass it on to my teammate Samuel.
Hi everyone, good morning. As we begin with our product, we first assess all the market requirements. As you can see, the device must be compatible with a panicus of grades 1 through 5. It must also expose the pelvic area, must not lower oxygen saturation, must require less than 10 minutes for application, and must not cause any adverse effects on skin, which led to the following design inputs. The device will sustain a minimum load of 60 pounds. The device will also move the panicus between 8 centimeters to 26 centimeters at an angle of 45 degrees. And it will also require only a maximum of 5 steps and a maximum of 2 medical staff per application while following ISO 10993 standards. As you can see, the next step was assessing the current products in the market. As you can see here, we have 4, and we have categorized them between 4 different criteria which we believe to be vital for a product of this type. The following are: does not cause skin irritation, avoid staphylor retraction, compatible with every paniculus, and also must expose the pelvic area. As you can see, most of these modalities only achieve 3 out of the 4, while our C product can assess all 4 of them, as they all rely on adhesive systems, which we do not. And as we progress through our project, we first began with design concept version number 1. As you can see, all these images have been color-coded for graphical purposes. The white intersection that you can see here was intended for biocompatibility. Increase the surface area of a really good biocompatible material, and thus decrease the chance for any type of adverse effects on skin. In yellow, you can see the adhesive, which improves grip of the device on the paniculus, and on blue you can see the canvas, which is intended to hold all the previously mentioned mechanisms and also cover the surface area of the funiculus. As well, you can see two straps in the beginning. This was upgraded and we performed a device design change, which upgraded to a 4-strap system with 2 straps at the top, which apply a force of equal magnitude on the X and Y component, and 2 straps down at the bottom that anchor down and fasten the funiculus. As you can also see, the interface was removed. This was because the selected material was strong enough to be both the canvas, and since it was biocompatible enough, we saw no need for the interface to still stay. Now I'll pass it to Danielle.
Okay, for our device, we considered a number of different materials, SMS polypropylene, polyurethane laminate, and neoprene scuba. We went forward with the SMS polypropylene, which is a fabric consisting of 3 layers, 2 spun bond, and 1 melt blown layer. This combination gives the fabric extra strength. It's durable, it's flexible, and for these reasons, it's commonly used in the medical field. It also has great antimicrobial properties, and best of all, it's inexpensive. We also looked into the adhesives for the grip onto the skin and went forward with the 3M9917. It's a soft cushioning adhesive that's gentle on the skin and doesn't cause irritation. Other components we looked into to provide further reinforcement, adjustability to the device. We added the strapping that's made from polypropylene, an elastic band, some hooks, and strap adjusters. To manufacture our device, we had to sew it together. This is the machine that we used, and it was easy to do. We were able to thread it easily, adjust patterns. It's very straightforward. And here we were assembling the device. We did have to make various adjustments throughout the process to tailor the device for the funiculus. Our final design output was this design here. It's 38 inches in width and 15 inches in length. On the bottom is an elastic band, which allows it to stretch to fit a variety of sizes. And in each corner are 4 seams where the straps attached to, and we made sure those seams are strong enough. Next, the Manicure.
So here we have a phantom model. We created this at the factory facility. It is we used it to be able to show how our device is going to work and to do the verification test. As you can see in the image below, the funiculus is hanging. It is composed of 3 main materials. First would be the dragon skin. It is the outer layer of a non-tacky silicone, and it's used for structure. And inside is encapsulated into the EcoFlex gel as a fat layer. It is soft and it mimics the fat movement. At the bottom, for stability, we have the ballistic gel at the bottom as the muscle layer. And this is placed on top of an acrylic board with hooks that are simulating the ones that are bolts and clamps that are found in hospitals. The size of this is half the size of a grade 2 funiculus in human patient in supine position. Then we have the prototype as mentioned before.
Here in the back.
Yeah. Okay, sorry.
Yeah.
As mentioned before, it has 3 main components. The first is the canvas in light blue is the SMS polycarbonate double layer. Then it has the adhesive, which is the 3M9917 on the sides of the device. At the bottom, an elastic band. And then our anchor system is all four straps in all 4 corners, a heavyweight polypropylene webbing, and at the end a swivel eye clip. Our device was designed so it could be holds from the bottom of the funiculus up, with the elastic band hitting a wider range of patients, and then most of the force being on the straps, since that's the strongest part of the device. Then it has top flap, which is for the medical staff to be able to handle the device without getting the gloves stuck to the adhesive. And it's a very simple, straightforward device that requires little to no instructions to put on. Then we did our simulation in Fusion 360. We've added all the mechanical properties for each layer and added a 60-pound force to the middle of the device. It was able to withstand without breaking, but we did notice a small deformation on the top corner, and this led us to
say is a weak point, so we added more verification testing that now Schneider is going to explain.
First test was a tensile test using a force gauge device. It was to determine whether the strap and the vertical hold to them together, since that is the weakest point of the device. Polyurethane laminated fabric and SMS polypropylene double layer both passed the minimum force required from our market requirements. Next test was the adhesive test. It was to determine the bonding strength between the fabric and the adhesive, and whether a bonding agent such as stage 3 had any effect on holding it together. The raw data for the different combination of adhesive, fabric, and the use or no use of this bonding agent stage 3 was collected, which analysis was performed. It was concluded for further analysis that the strongest combination was polyurethane laminated fabric, adhesive 9917, and the use of stage 3, followed by SMS polypropylene double layer, adhesive 9917, and also the stage 3. Next, we have the load bearer test. It was to determine whether the device can actually hold the 60 pounds with no deformation or tear over time. As you can see on the image to the left, the device with the load. As time goes by, we increased the load. 77 pounds was the maximum what we had. And as you can see right here, that on the right, the device showed no deformation or tear during the test and after. Next, we have the phantom verification. We actually address the phantom model, as you can see here, with the device and measure the displacement. The maximum displacement we measure was approximately 26 centimeters, and the minimum was 21 centimeters. The cost analysis. The total material cost to fit the device was $17.83, $25 an hour, and $12.13 was offered. This leading us to a product cost of $54.96. Our total budget given was $2,000, and most of it was used on materials. Our device is a class 1 device, meaning they pose low to moderate risk to the patient. For the same reason, it is 510 exempt. Our global engagement standards include ASTM and ISO standards related to grab and strip tests, quality management system, application of risk management to medical devices, and biocompatibility. Next, we have Daniela for global awareness.
So obesity is a growing global concern. According to the World Population Review, obesity has tripled in the past 4 decades, with some of the highest rates in Samoa, Jordan, United Arab Emirates, New Zealand, and the United States. The future goal of this project is to provide better abdominal retractors for the morbidly obese patients so that they have a better experience in the surgical room. Given that the seat retractor is a low-cost, lightweight, and disposable device, we are hopeful that it can make an impact in any part of the world, and Camila will now complete the presentation.
So we have been able to manufacture a device that can hold 60 pounds, is able to expose the pelvic area without capillary traction, and targets a wide range of patients. Seat is able to expose and improve the visibility of the patients while also enhancing the patient and user experience. The next step for the project will be patient testing and also reducing preoperative and surgery time. Now to finalize, a special thank you to our sponsor, Thyroid Engineering, so Biomedical Engineering faculty, and our fellow classmates for this opportunity and the continuous support. Thank you for your time and attention, and now we're ready for questions.
Thank you. We have time for 2 quick questions from the judges.
Quick question. With regards to the design inputs, can you explain to me how you derive that 60-pound minimum load requirement?
How did you get the DI for 60 pounds?
So first we started with everything is based on literature values, mostly our research papers, and from where we got the clinical specification was from our literature article in which it was a paniculectomy based on paper. And from there, we got the weight that's from 11 pounds to 120 pounds, but that's with gravity included. And since the patient is laying down, the weight is distributed. And I believe there's also a paper in which it said, in which they did a paniculectomy, in which just a panicus weighed 20 pounds. And as recommended by the sponsor, it was suggested to multiply it by 3.
One more question?
I have a question. Thank you for the presentation. One question I had is, what kind of issues would you think you have as you start to scale up the operation of producing these devices? You have very good tests. What kind of pain points do you think you'd have as you scale?
Can you repeat that, Dr. Thompson, please?
Yeah, the question is, what kind of issues do you imagine you may have as you begin to scale the production of these devices?
Yes, how do you go from prototype to scaling this? What can
The
you?
only one that I can think of is assembling the different parts. You have hooks, strap adjusters, different materials. You know, that might take a little more time to assemble. Besides that, I can't think of anything.
A couple extra comments that I would say would differ between the prototype and manufacturing is that manufacturing, of course, it would be sterilized. We got from our sponsor a recommendation for ETO sterilization. And what's also really interesting and very good about the material that we chose is that we can also treat it with different components and achieve different results that would improve biocompatibility and different type of surgery or like more specific type of treatments that can treat blood, not repellent, but blood compatible and things like that. So that would be the only difference between what you see here and manufacturing.
Okay. Let's give it up for Team 6. I'd like to invite Team 7 to the stage. 3D CPM device to restore elbow mobility. Sponsored by Bioengineering Labs. Consumers is the faculty mentor. David Barbosa, Isabella Davila, Armando Hernandez, and Daniela Polo.
Good morning, everyone. We're Team 7. My name is Daniela Polo. I'm Isabella Davila.
I'm David Barbosa and Armando Hernandez.
And today we're going to be presenting our senior design project, a 3D continuous fast motion device to restore elbow mobility, also known as 8135, sponsored by Bioengineering Labs. So everyone in the audience has either a family member, a friend, or a neighbor who has suffered the debilitating effects of a stroke. Some of the effects of a stroke include paralysis on either side of the body, memory loss, and speech and language problems. If you know how complicated the life of a stroke patient can be, then you will be pleased to hear that our project tries to find a better quality of life for patients suffering from elbow paralysis, giving them a second chance at rehabilitation. Clinical research reveals that early intervention and consistent therapy greatly improve the chances of recovery. The aim of our sponsor and our project is to bring a new CPM device to the market that will address the drawbacks of current rehabilitation methods, which include high cost and low accessibility. The clinical need demonstrates that 77% of stroke survivors suffer from upper limb paralysis. Most of these patients need additional support once they get discharged. Our device will be able to provide the necessary. Our device is going to be able to provide therapy at home in the hopes of improving patient compliance with treatment and the chances of recovery, as well increasing with muscle activity. The market background demonstrates that more than 795,000 people in the United States suffer from stroke yearly. The current CPM devices that are available are not as accessible because of the high costs, and they're not really portable. The physical therapy is another approach that could be used to restore mobility, but this is also very expensive, and it requires patients to attend sessions that can cost $325 without insurance. It should also be noted that the CPM market is expected to increase 8.5% by 2026. And next is Armando with current modalities.
Thank you, Daniela. Current modalities for rehabilitation of the elbow include physical therapy and CPM devices like Kinetic 6080 and Anthromo D2. Physical therapy is the most customized modality. However, it is also the most expensive, and the patient's ability to recover will depend only on the skills of the therapist. On the other hand, CPM devices are not only expensive, but also heavy and bulky for the patients to use them without any assistance. Our market requirements were carefully selected to fulfill the needs not met by our current modalities. First, our device must withstand at least 3 times the force necessary to complete a full range of motion, which is translated to a force of 60 newtons applied at a distant end of the device. Since our targeted user is a patient with muscle weakness or paralysis, the device must be light enough to be carried and supported for the patient. Therefore, its weight cannot exceed 5 pounds. Establishing a therapeutic range of motion was a priority. So the option to select a smaller and lighter range of motion was included in the device. Okay. Excuse me. Overusing the device was another priority that we considered. So a design input was implemented to limit the total time of therapy per session to 1 hour. Safety was a top priority. So 2 requirements were that the device must have safety features to avoid overextension and overflexion, as well as to stimulate muscle activity at an acceptable angular velocity. Now I'll pass the word to Dave.
Thank you, Armando. So we began our concepts by first acknowledging all of those design inputs that we had laid out. So at first, that meant emphasizing creating a frame that can both be easily mounted and adjustable. So like you can see in concept 1, we originally had a circular arm support system, but it was deemed too difficult to weave the patient's arm through those hoops. So we opted for a more open design instead, like in concept 2. This concept would use a linear actuator to power and would rely on the physical limits of the motor itself to serve as those safety stops. But there were issues with versatility and with a lack of motor power, so we made a couple of changes to arrive at our concept number 3, or our MVP. This design would use a DC servo motor, which would allow for precise angle increments without sacrificing power. It also allows us, it's also adjustable to various sizes and shapes, and allows us to implement the software and physical safety stops to prevent that overextension or overflexion that we don't want. Before manufacturing, we conducted SolidWorks simulations of the most critical parts of the device. This included the physical safety stop and the motor mounts, since they would be subjected to the greatest loads. Results showed a factor of safety greater than 1 for all of the critical parts, meaning that our device would not fail. For our prototype, we manufactured it using 20% carbon fiber PLA. For a patient to use it, they would select the arm that they want to use, then the modality to start the therapy, and if they choose to stop before the allotted 60-minute timer, they can press a red button to stop it. Therefore, our device would provide affordable physical therapy in the form of repetitive flexion and extension exercise of the elbow, all while mitigating the risk of harm. For our subsystems, we used a wide range of materials. Like I said, we used carbon fiber PLA for the 3D printing material. For the motor, we used a 180 kilogram per centimeter DC servo motor, and the power supply is a 12-volt DC to DC adapter. To control the system, we used an Arduino Leonardo along with the Arduino software. And for the visual feedback, we used different colored LEDs to indicate which setting was selected. And I'll pass it to Isabella to continue with our verification testing.
Thank you, David. So 7 verification protocols were performed. The first one was to weigh the fully assembled device, and the A135 successfully met the design input with a weight of 3.06 pounds. The second test was to verify the accuracy of the 2 range of motion modalities of 115 degrees and 58 degrees. The measurements were taken with a goniometer attached to the device, which was set to run 5 times back and forth for each modality for each arm. The test found that the device successfully makes the range of motion movements with a 95% confidence interval of less than 1 degree. The third test was on the software stop mechanism that will prevent patients from using the device for more than 60 minutes continuously. The test was run 3 times for each range of motion modality, and the test found that the software successfully stopped the device at the set time with a 95% confidence interval of less than 1 minute. The fourth test was to ensure a safe angular velocity of 50 degrees per second as established in clinical research. As you can see in the video, The measurements were taken with a electric pencil attached to the device that tapped the timer every time completed the range of motion movement. Additionally, a goniometer was used to record the exact angle movement. These two measurements were used to calculate the angular velocity, and a safe average angular velocity of 50.9 degrees per second was achieved, with a 95% confidence interval of just 1 degree per second. The A135 had to overcome 2 Peter tests. On the first one, it successfully demonstrated to have a safety factor of 3 by lifting a weight of 7.81 kilograms 5 times. The second killer test was on the mechanical safety stop included on the design, which successfully prevented the motor from moving beyond the range of motion limits. Finally, the team verified muscle stimulation during therapy with the A135. This was done by performing an electromyography of the bicep and tricep muscles on a healthy subject at rest, during active movement, and during passive movement with the A135. The pair test results between the relaxed position and the passive motion with the A135 allowed us to reject the null hypothesis with a significance level of 0.05, which demonstrates a significant difference between muscle activity at rest and muscle activity during therapy with the A135. Additionally, the integrated EMG data of the bicep and tricep muscles during active movement and during therapy with the A135 demonstrate a similar activity pattern, giving the team further reasons to believe that the device is therapeutic. Now Armando will follow with the task analysis.
Thank you, Isabella. Initially, the team was granted $1,500 for the completion of the project. After assembly, we were able to calculate the product cost, which was $207, and obtaining a profit of $200, the retail price of the product would be $620. For the regulatory assessment, A135 is considered by the FDA as a medical device class 1 because it doesn't, it is a low risk for the patients. Now, David will continue with global engagement.
Thank you, Armando. So in order to be truly successful in this project, we have to constantly keep in mind global learning initiatives. So although a majority of strokes occur in patients 65 years and older, it can happen in anybody. And of those survivors, about 80% are affected with upper limb paralysis or weakness. It's also really important to know that there's an ongoing worldwide shortage of physiotherapists, which is creating a higher demand for simple therapeutic devices that can either assist or replace them. That's why it's imperative to create a cost-effective, practical, long-term treatment plan for patients who suffer from the debilitating effects of a stroke. For perspective, we kept inclusivity in mind while designing our prototype. That meant affordability, adjustability, and ease of use were all key factors when deciding on our final design. That way, patients from various socioeconomic backgrounds and various shapes and sizes can all benefit from our device. And I'll pass the floor to
Thank you, David. To summarize our accomplishments, we were able to successfully use the resources by the BME department and their sponsor, as well as use the knowledge obtained in our BME curriculum. Here we can compare the A135 to the other current modalities, and we can see that not only does A135 provide therapy at home, but it also has features that the other current modalities do not have, while still maintaining a lower cost. In the future, more modalities could be developed so the therapy could be a more personalized one. Additionally, an app could be also developed to control the device and obtain data from the progress of the patients. The weight could also be reduced through material selection, and the arm supports could be made with a more pliable material to make it more comfortable for the patients. We would like to thank and acknowledge all the following people that made this the best experience possible and the project successful. Thank you.
Running a little bit behind schedule, but we do have time for at least one big question, maybe two.
I have a question. The device that you just designed, it is really great, especially for a user to be able to do it at home. However, the device is only like, just the forearm, right? but the people with the, for example, the stroke patients, the entire arm would be affected. So why you guys limited only the device with just a forearm, not considering the entire arm?
No, the device does consider the full arm. It would be extension and flexion of the elbow. So it does mount on the upper arm and attaches itself to the form as well.
But does it work for like a shoulder movement, the upper joint of the arm?
No, it won't.
No, it's targeted for elbow immobility, but overall it enhances the movement of the whole arm. Either way, for the stroke patient, most of the paralysis is either on the elbow and shoulder, but the device is targeted for elbow immobility.
Thank you very much. Vani, did you have something to add? Thank you very much, Team 7. I now call Team 8 to the stage. Acetabular cup implant adaptation. Sponsored by Exotech Corporation, faculty mentor, Dr. Raj. Team members, Leticia Fonro, Eddie Colero, Samir Nasser, and Lorraine Sierra.
So good morning, everyone. We're Team 8 and we're presenting the acetabular cup implant adaptation. Total hip arthroplasty is performed when the patient's hip is so severely damaged that they're in pain even while resting. Common reasons for this surgery is osteoarthritis, hip femoral head fractures, or hip dysplasias. The procedure begins by making an incision on the affected hip. Once the femoral head is in view, the surgeon will remove the femoral head and ring the acetabulum. The surgeon will then take an impactor, like this, and connect it to the cup. Follows. And then they'll hammer it into the acetabulum. The cup has a porous coating on its surface intended to fix onto the bone. When the surgeon wants to adjust its angle, he has to apply a torque force, levering it forward or rotating it. Oftentimes, like 5% of the cases, the impactor disconnects from the cup when the levering action is done. And it lacks in rotational control. As you can see, the impactor rotates right on the cup. So this prolongs the surgery by 15 to 20 minutes, increasing the risk factors for pneumonia, bleeding, and infection by 14%. We found that $68 per minute is the cost of an average operating room. Multiplying this by the amount of times that the impactor disengages and the time, we found that $372,000 was wasted due to the impactor disengaging prematurely. Solving this issue can make our sponsor one of the top competitors in the market. So as you can see in the video, as I explained earlier, the impactor has no rotational control over the cup, and it also lacks in levering control. So our proposed solution is to design a component for the impactor that will provide rotational and levering control over the cup to decrease the surgical time. Now Leticia will explain the market requirements.
A survey was conducted to identify the set of requirements that our device must meet. Our device is expected to enhance the mating strength between the impactor and the cup. It's supposed to provide rotational control. Our device is also expected to be durable, not hinder the impactor's main function, and allow the surgeon to move the cup in the desired position. To meet this market requirement, we went with some design inputs like it should withstand a force of 200 to 300 pound/inch when it's being moved, and the impactor should stay connected to the cup when that force is applied. It should reduce the reattachment time to less than 5 minutes. Young's modulus for our material should fall in the range of 190 GPa to 210 GPa. Our Rockwell hardness of our material should fall in between 23 to 40 HRC, and our cup, when being impacted with our device, should not extrude for the hip for more than 1 millimeter. comparing the current model to the one that we have with our device, the current model successfully impacts the cup to the hip. It also allows for a posterior approach, which is mostly favored by some doctors. But unfortunately, as we mentioned, the impactor disengages from the cup unexpectedly. It has little to no rotational control, and it has long re-engagement time. With our device, we're able to meet all the limitations above, but we had some challenges in the fact that our device reduced the field of view of the surgeon, and it also, the material of the cup appeared in the imaging of the intra-op radiographs. Next slide. Now, Samir is going to go ahead and explain our design concept.
All right, so for our first design concept, it consists of a ring that fits over the tip of the impactor. We added a push pin mechanism that fits into the side of the impactor, but due to the high forces applied during standard surgery and the low contact point, like low surface area of contact between the push pin and the impactor, it would cause damage to the impactor. So onto our second design concept, we decided to abandon the push pin mechanism and move forward with a casing that fits over the impactor's fixed sides. This fixed our rotational control, but it also had weak points within the ring at the rods, so it would not withstand repeated use. So onto our third design concept, we have we kept the casing mechanism, and we also have two wing-like projections that have four semicircle extrusions that fit into the rim of the cup. And we removed the bottom part of the casing due to it bringing up manufacturing costs and not contributing to the overall function of the attachment. So these are our design specifications. So for the more, for the design, for the parts of the design that required more accuracy, we used a tolerance of 0.01 inches. And for the parts that were more cosmetic, we used tolerances of 0.02 inches or more. As you can see, this is our device's mechanism. It's quite simple. The attachment slides onto the tip of the impactor, and the impactor attaches to the cup implant. So all our simulations were ran with the thought that with the idea that the maximum force is applied during standard surgery. So first we have our impact simulation, which simulates the highest amount of forces applied during standard surgery while the surgeon is impacting the impactor. Second, we have our rotational simulation, which simulates the highest amount of force applied to the attachment while the surgeon is rotating the impactor. And finally, we have our levering simulation, which simulates the maximum amount of forces applied during standard surgery while the surgeon is levering on the impactor. All these simulations were done in SolidWorks, and we used the material stainless steel 17-4. Now until teach technology assessment.
Our device is made up of two parts. We have the out-end attachment and the O-ring. The out-end attachment has two wings on different axes, and each wing has four projections. The two wings are filated in order to spread the stress on our part, and the four projections fit in the cup scallops in order to provide rotational control. We have a central cylindrical opening that permits the impactor to go through and meet directly with the cup. In that cylindrical opening, we have a central groove that allows the O-ring to fit in and secure the impactor to our part. The O-ring is 1.6 millimeters of thickness and has 16.1 millimeters inside diameter. Next slide, please. For manufacturing, we decided on stainless steel 17-4. We compared it to different materials on the market, and we decided that it fit our criteria in that it had strong tensile strength, it was good, it has good corrosion resistance, and it's readily available on the market. We decided to CNC mill our part, and we decided to heat treat our material at 900 degrees for 1 hour to enhance the material's mechanical properties. And also we decided to light bead blast it to give it a smooth finish. For O-ring, we decided to order it from the manufacturer to reduce our production costs, and we settled on the nitrile rubber due to its nitrile rubber basically has superior tear resistance. Next slide. For cost, our material is expected to cost $283. We had a total budget of $5,000, and we came out with a total budget use of $1,814. You can see this is a bigger view of our finished part. And in the video, it's an assembly with our part, the cup and impactor. You can already see a big improvement in rotational control. And now Eddie is going to explain our benchmark testing.
All right, so for the first verification test, we ran a repeated impaction test. For this test, an Exactech engineer connected our piece onto the tip of an impactor and then connected the impactor onto a cup. Once this was complete, they then put the impactor and the entire setup into a sawbone, as you can see on the picture on the right side. Once this was finally set up, the exacting engineer would repeatedly impact with a mallet the impactor for a total of 875 times. For acceptance criteria, all these, they would have to survive all 875 impacts without any signs of fracture. As you can see from our results, there's only minimal wear and no signs of fracture with our piece. The second test we ran was a torque out test. We used the exact same setup as I previously mentioned, but instead of a sawbone, we put it on an immovable plate. And then once this was set up, a machine will then provide an axial force onto the impactor, trying to disengage the impactor from the cup. So for the acceptance criteria for this, we require like a higher axial force with our piece attached than rather without the piece attached. As you can see from the results, the average of the average axial force with our piece almost doubled every single time. And then finally, for the last test we ran a tolerance stack test. A tolerance stack test, basically the dimensions and tolerances of two pieces are compared at worst case scenario. So for this first table, we ran it with our piece and a cup. As you can see, it passed nominal clearance and least material conditioning, but it didn't pass the most material conditioning. The red box indicate a failed test. And one reason we can do this to fix this problem would be to just readjust our tolerances and rerun a tolerance stack test. Finally, to continue the tolerance stack test, we now got our piece and compared it to the impactor's tip. We are mostly concerned with the third bar here, which is the offset impact that we previously mentioned. We're happy to say that I was able to pass all 3 tests for that. After that, we continue to run the tolerance stack test for different impactors because our company wanted to see how it would work with other impactors. Unfortunately, I wasn't able to pass one of the tests for the Novation straight impactor, but just like I previously mentioned, we can fix that problem. And then for global engagement, here you can see the various international standards we use for manufacturing, testing, and cleanability. And now into Lorraine with global awareness.
So in the United States in 2017, there were about 450,000 cases performed according to the Healthcare Research and Quality. In Europe, there were about 650,000 procedures performed in 2017, and this is projected to pass these 700,000 by 2024. We conducted a patent search and didn't find any devices similar in the market, so we suggest that our sponsor goes ahead and patents the device. In conclusion, our team was able to create an attachment piece for the Alteon hip system that reduces operation time, increases the rotational and levering control of the cup, and is able to successfully implant the cup in the hip. We were able to complete the project under budget and in time. Thank you so much to everyone who helped us along the process, including our sponsor and the FIB department. Any questions?
Time for a couple questions.
Sure, I was asking if they can give some insight into the regulatory classification of this device.
Regulatory pathway.
Yeah. And what would we
Regulatory
need
pathway for this device. You speak to that. What would be the pathway to approval?
So it would be a 510K exemption. I think it's class 2, if you remember correctly.
Okay. Any other question?
Yeah, I've got one.
Dr. Thompson.
You can go ahead, Brian.
Oh, okay. What kind of hurdles do you think you'd encounter for market adoption? You know, you have a device, you want the surgeon to use the device. How would you convince them this is a better device for the current standard?
Pathway to adoption. How do we get it from your bench top into the market, and how do you, I guess, influence the market? And this is the device of the future.
So the biggest hurdle we're going to have with that is currently it's the impactor and just the cup. So if we're introducing our piece, that's going to be a new strategy that the surgeon would have to use to go into surgery with. So that requires them to relearn a new process with something they're already familiar with. So that'll be our biggest hurdle, trying to convince surgeons to completely switch their way of surgical operation.
Yes, ma'am.
And another thing, our company, the company we work with, Exatech, has come up with a new way of mating the cup to the impactor. That's like the mushroom fit. This mushroom fit is basically a new, it's new on market, and more doctors are starting to use it. As we said, it's about 12,000 that we're producing, 12,000 that are being used, like doing procedures every year. So we Exatech's amount of like clientele, we expect them to switch to that. And then this part is mostly specific for that mushroom fit because that's a problem that's with that. And although some tests were run with other impactors, and they showed like it really helps. It actually does work with other impactors and other ways of mating. So
you're predicting a smooth transition.
We're predicting a smooth transition with this. It will be a smoother transition, and more people will switch to that.
Finally, Team 9. I'd like to call Team 9 to the stage. Fibula, guide for wire. Faculty mentor, Dr. Nick Tsoukias. Sponsored by Anthrax, Pedro Julia, Paulina Alvarez, Eliana Ruiz, and Annette Sanchez.
Hello everyone, we are doing live and our project is called People Guide for What is sponsored by us. During the fibular nerve surgery, nail placement is on the guide wiring section, which is the most time-consuming aspect because it is often placed too medially or too laterally. However, current solution rely on incorrect initial placement. We designed an add-on that we could do the initial section of the K wire and direct the correct trajectory that the nail will move out beside the medullary canal. Concept learned through different BME courses help us with the frameworks to analyze the physical guide, the mathematical theories, and apply medical procedures, and also with the programming. Around 673,240 ankle injuries per year in the US, and there are more than 90% that go to distal fibula. Current solutions had high complication rates, but fixation, but intramedullary fixation, it's less invasive and it decreases the risk and the complication. Due to its benefits, it helps to high-risk patients, militaries, and athletes.
Okay, so for some context, let's talk about how the procedure is currently working. So the first step of the surgery for the fibulog system is to insert the K wire. This K wire is inserted based on an initial guess by the surgeon, and that initial guess is in terms of point of entry and also angle of entry. Then during surgery, they use real-time fluoroscopy to check that the wire is in fact located in the center of the medullary canal. Given if it's the case that the guide is placed incorrectly, and by that I mean too medially or too laterally, then the surgeon needs to extract the K wire and place it again, basically following this trial and error method. So as you can imagine, this is not very effective and it's very time consuming. In fact, 7 out of 10 surgeons place the K wire incorrectly on their first trial. Therefore, there is a need for a method that could guarantee the correct placement of the K wire. This would remove several time barriers and increase the efficiency of the surgery, which will result on surgeons being able to adapt this. However, there are no current guides that have been adapted by the majority of surgeons.
All right, so Annette has highlighted the benefit that a guide would pose for art. So you might be wondering why they haven't addressed this problem. They have. There's currently 2 devices to help with wire insertion. The guide wire offset guide, it allows for correction based on an initial placement, 2.5 to 5 millimeters from that initial guess. However, it does rely on that incorrect initial placement. The fracture finger, it aids with wire insertion when it is stuck in the medial cortex. However, it does need to be removed before drilling, meaning more steps are required, and it does not define the entry point. So based on what hasn't worked and based on surgeon feedback, we came up with these Manicure requirements, which revolve around being reusable, being adaptable to different patient anatomies, complying with current standards, and sustaining sterilization. Hence, our project scope was to design an add-on for the fibular nail system to ensure that the K-wire is correctly inserted and placed by December 2021 with the tools and resources provided by the company. To approach this problem, we had to apply different concepts from theoretical concepts like anatomy and bone histology up to more technical concepts like image processing.
All right, so we already talked about clinical research and market research. We'll now focus a little bit more on assessment, design, simulations, and evaluations. All right, so our clinical research led to the creation of these design inputs. First of all, it has to ensure accurate placement, but without interfering with porosity imaging, which, as Annette explained, is used during the procedure. To ensure material economy, it has to be reusable. The guide has to be reusable. That means it has to be sand sterilization, and it has to comply with current standards and regulations. For the purpose of our time together, we will focus on the design inputs that are in bold in the slide. First of all, the guide had to fit pre-existing surgical components. That meant it had to fit both the guide wire and the drill, and it had to simplify surgical procedures. That meant it had to be easy to grab, easy to handle, and it had to withstand handling forces. When looking at this design inputs, we came across different hazards that had to be taken into consideration. These revolved around improper device functioning, allergic reactions, or possible resulting injuries. These could be controlled with detailed surgical steps, proper material selection, and extensive verification. Pedro will now talk about the process of our designs.
When it came to the initial design concepts, we relied mostly on the anatomy of the lower leg in order to create. And in doing this, we actually developed some key concepts that we wanted to keep for future steps or future design concepts. So in order to do this, we focused on these three things: essentially the easy use of the device, and the placement or the correct placement of the wire, and the correct placement of the pad. This right here is a great example of us doing just that. For example, this design concept had a set angle, and this set angle actually made the wire placement more accurate, and it's because it removed one of the two key aspects of the insertion point from the doctor's hand. Essentially, now all the doctor had to worry about was the location. Then, when it came to our final design concept, we also used a similar process to get there. And essentially, that allows us to get all these key features, including a handle that increased the ease of use of the device, and then the angle, which obviously increased the accuracy as mentioned previously, and then these K-wire like rods here, as you can see, that actually increased the use of the device because now it could also guide the K-wire and the reamer. And as I mentioned, this tip down there that actually helps keep the guide in place when the surgeon is using it. Now, to finally get this final design concept into like an actual model, there's one step that we had missing, and it was actually the image processing. Essentially, we use the fluorescence imaging given by Arthrex that Annette and our previous members actually mentioned, and we used this to develop an angle that was about 12 degrees. Then we also got improvement based on surgeon feedback. In doing this, we actually decided to increase the rod length and increase the handle length in order to increase the ease of use of the device and to also increase the protection of the tissue in the surrounding area. When it came to the selected materials, we decided on several types, including materials and polymers. But in the end, we ended up choosing stainless steel 360, and this is due to its biocompatibility and durability. Now, when it came to machining, it was a similar process in trying to decide. We went through several options, including CNC machining, 3D printing, and overmold. But in the end, we ended up choosing these methods seen here. And the reason is because of their cost effectiveness. For example, in this form bending method, we just had to cut out a piece of CNC machining, and this thin sheet of metal. And essentially, I had to clamp it down, and then we bend it into the shape of the handle. And then next, spin forming was used in order to spin this raw material in a quick succession in order to get the shape of the outer diameter. And then the inner diameter was made by drilling into the rod. Afterwards, welding was done to basically pair up the outer reamer rod and the handles together. And this actually increased the strength of the rod and improved the weak point that we might have had. As you see here with the several simulations, I were to find that based on these manufacturing details, the rod would in fact be with all the forces that a surgeon will apply to it during surgery. And not to mention that it also should last for the 2 years of the lifetime these products usually have. Now, for the product cost, the cost was more or less $545 to make. However, it's important to know as this is mass produced, that price may decrease down significantly. And not to mention that this price is actually already much lower than the current modalities that Arthrex uses, which are above $900. Now, as for our product budget, we technically didn't have any direct budget from Arthrex. However, they did provide all the material costs, all the manufacturing costs, and then the shipping costs.
Okay, so as this was a class 1 device, there was no strict regulatory assessment needed. We did have to comply with regular standards such as labeling and biocompatibility. We also had to ensure that the design inputs were met. So in order to verify this, we used a total of 4 3D printed PLA units. And for the time being, for time purposes, we're gonna mention a couple of these protocols that we think are good examples of the types of tests and are also representative of the types of tests that we use. So for example, to measure the inner diameter of the rod components, we use a caliper as shown here. Out of the 3 rod components, we're just gonna focus on the gate wire as the rest are repetitive. So what happened is that each team member measured the diameters separately, and then we averaged the results to reduce biases while measuring as shown in this graph. The acceptance criteria for this test was met as at least 95% of the tested diameters were equal or more than 1.70 millimeters. Another very simple test was to weigh the samples. And in this case, we used the density of PLA to establish a conversion ratio to stainless steel, which is the actual material that we used for prototype. In this case, the acceptance criteria, though with the mean of the sample, that had to be less than 71 grams, and the standard deviation had to be less than 1 gram. And as we can see, this was also the case. This was a more complex protocol when, in order to test the ability of the handle to withstand circumferential forces, we first used a dynamometer before applying actual force to the handle. So we did this in order to establish this graph that shows simultaneous EMG for activity and clench force. Then using MATLAB, we established a correlation between the 2 variables to be able to estimate clench force from EMG data. This is an example of one of the units that we tested that shows the estimated force from the previous coefficients that I just mentioned that we found. So to determine if the acceptance criteria was met, we measured the width and length of the diameter of the handle before and after applying the force to determine if there was a significant deformation. So to determine this, we used a dependent t-test to see if there was a significant difference between the mean measurements of each group. In this case, there was no significant difference at a 95 confidence interval, which indicates that there's no significant deformation before passing the test. So if we go back and look again at the project, we can see how our first accomplishment were establishing market requirements from the market research that we performed, then translating those market requirements into design inputs, then materializing those design inputs into a design concept, then taking into account a design for manufacturing approach, and then verifying that prototype in fact made the design inputs. Moreover, we were actually able to test our guide during surgery and a cadaver test by surgeons, and they were able to pass the KY and to drill to our guide, which indicated that in fact the guide could be used for surgery, and therefore passing also the kidney test, and in a way also providing feedback. Finally, our milestones start with our written proposal, the initial proposal a year ago, and end with the prototype verifications that we just talked about. Global awareness included taking into account the disadvantages of previous methods that led to the creation of the fibula, and global perspective also took into account economical, sociological, and clinical aspects that led to the improvement of this device and also the need for this guide. So we want to thank our sponsor, Artrex, specifically Alex de Monaco. We also want to thank Dr. Christie, Dr. Sukian, and Dr. Shahistani for their constant support, and thank all our classmates for staying until the last minute.
I think we have time just for one big, maybe 2 small questions. After this, we're going to switch off and go to the Panther pit for the poster presentations, which will be by a different jury. So any questions for team number 9?
I have a question. What sort of additional testing do you think will be required to prove that this device is indeed, truly reusable?
So there's one test that, reusable? Oh, so definitely like the test that we had to, it was like melting point of the material, pressure that it was, yeah, so like, because we thought about autoclave, so it's basically pressure and.
Speak to the camera.
Oh, yeah, special pressure and heat temperatures. Yeah, so question there.
I'd like to hear another question. More questions?
It is impressive that you guys are able to design a device where a surgeon can use it and have a preliminary results how effective it is. However, like, there was a question about reusability is one thing. The second thing is, since it's in vitro device, right? It's entering into a human's body. So over it, like if the device is reusable over a time, what would be the because it has to go through sterilization and all, what would be the material constraints?
So our material choice, stainless steel 316L, it was taking into account that it had to be sterilizable, so reusable, but also be compatible with the other existing devices in the surgery. So by ensuring it's the same material, we're removing the possibility of galvanic corrosion, and this device is only introduced a couple of minutes. So just by ensuring that it's sterilized and that it's compatible with the other metal parts, it should ensure that it's safe to be used in surgery.
I'd like to thank Team 9 and many thanks to our judges for your hard work. It's time for sequestration and deliberations. So.